So dear all, welcome to our next RKHS seminars. And today our speaker is Arthur Grethen from GASP Computational Neuroscience Unit, Center for Computational Statistics and Machine Learning at the University of College London. And today's talk is going to be on causal effect estimation with kernels. If I wish to explain a couple of things about Arthur Grethen is a professor with the GASP Computational Neuroscience Unit and also director of the Center for Computational Statistics and Machine Learning at UCL. He's a research scientist at Google DeepMind. He received his degrees in physics and systems engineering from Australian National University and a PhD with Microsoft Research and the Signal Processing and Communications Laboratory at the University of Cambridge. He previously worked at the MPI for biological cybernetics and at the machine learning department, Carnegie Mellon University. His recent research interests in machine learning include causal inference and representation learning, design and training of generative models, and also non-parametric hypothesis testing. He is very generous for giving a talk in this series, so I will leave the word to him. Thank you very much once for coming.
Okay. Oh, well, thank you for inviting me. So yeah, I'm very, very happy to be on the talk. Oops, let me, I'm not sure why that happened, but I'll stop that. Okay. Hopefully that's not going to, it's going to, sorry, that should work. So the topic of this talk is on causal modeling with kernels. So I should emphasize as well, like I really like to get questions during the talk. Please just interrupt me. I'm not able to see the Teams link at the same time as the presentation. So just interrupt me like verbally, just ask a question if any question comes up, and I'm happy to answer at any time. Okay, on with the talk. So I'm going to start with a simple medical treatment scenario where we're in a hospital treating a particular disease, and we have one of two treatment options. So we're either treating with pills or we're treating with surgery, okay? And as a result of this treatment, which the doctors prescribe, then there's a patient outcome, which is that the patient is cured or not, okay? Now, let's say that we've observed historical hospital data and we've found the following conditional probabilities. So the probability of being cured, given that pills were prescribed, is 0.85, and the probability of being cured, given surgery was prescribed, was 0.72. All right, so those are the statistics that we got from observing the hospital. And now let's say I'm a hospital administrator, and I look at these statistics and I say, well, look, pills are cheaper, pills are more effective, right? From now on, everybody gets pills. So what have we done wrong? Well, let's say that we now intervene, okay, so with the hospital administrator, and we've now said, okay, we're making an intervention. We're requiring everybody to get pills from now on. So an intervention is shown graphically here as a node with a double boundary around it. And the result of that intervention, so the result of saying everyone gets pills, is a y with a superscript, which is equal to that intervention. So the choice of giving everybody pills. Okay, so this intervention, let's say the hospital administrator has made this intervention, the probability of being cured given the intervention pills is 0.64. The probability of being cured and given the intervention surgery, so if the administrator said everyone gets surgery, is 0.75, right? Now these numbers are not those numbers, okay? So what mistake has our administrator made in making this intervention, in saying, look, if I gave everyone pills, then I'd get a cheaper and better outcome, okay? What the administrator has forgotten about is the context in which the doctors are taking their decision. Okay, so what I'm showing here now is a little bit more detail about the system that's going on in the hospital. So X is actually the severity of the disease. So the disease can take two forms. It can take a mild form or a severe form. Now, based on the severity of the disease, the doctor's going to look at the patient and they're going to say, look, I'm going to prescribe pills or surgery, more likely pills for the mild form, more likely surgery for the severe form. And then resulting from the severity of the disease and the treatment, we're going to get the recorded outcome, so the historical outcome, okay? And those that whole system is going to give us this result at the bottom of the slide here. So how are these equations obtained? Well, this is how these equations are obtained, okay? So basically, what am I doing? I'm taking the conditional mean of being cured, given my treatment, and given the severity of the disease, and then I'm weighting it according to this. So let's say that we've observed that pills were prescribed, right? So A is pills. Given that we've observed that pills were prescribed, it's more likely that the form of the disease was mild, right? X is mild. It's less likely that X is severe, okay? And so then I'm taking the weighted sum of chance of being cured given treatment and severity with more weight for the mild form and less weight for the severe form. That's how I'm getting this number here, okay? So more likely people with mild form have been prescribed pills, but it's also more likely that people with mild form are going to get cured. Conversely, let's say that surgery was prescribed. Well, then it's more likely it was a severe form, right? So given surgery was prescribed, I give more weight to severe, less weight to mild, and then I take the mean, the weighted mean of y given nx with this weighting here, okay? And so this is going to give me this number here. People with a more severe form are also, of course, less likely to get cured, okay? So now let's look at the intervention in this system. So here's our intervention. So it's a node with a double boundary. Here is the A. So this is the earlier observed distribution. Okay, so this is the results that we recorded. But notice that the intervention A is now decoupled from X, right? I'm a hospital administrator. I'm saying everybody gets pills, right? Do pills means everybody gets pills. Now, what is the chance of being cured under this intervention? Well, in this case, everybody gets pills, right? So whether you've got a mild form or a severe form, you get pills. So here is the equation that governs these results down here. And you can see you've got, again, the chance of being cured given the treatment, given the severity. But now I just take an average over my population. So I call this my average causal effect or my average treatment effect. This is just the average result of a particular action on average over my population, okay? And you can see that when I take that approach, this interventional approach, now I'm getting very different answers than my observational approach. Okay, so this is to explain, I think, both graphically and mathematically, the distinction between observing a system and intervening on a system. Okay, so the goal of this talk is basically from observational data, okay, so from observing this system, we want to make predictions on what would happen when we intervene on a system, right? We're going from observation to intervention, okay? And we're going to approach this topic using kernel methods, okay? Now, first of all, I'm going to talk about the average treatment effect or average causal effect. So that's what I described on the previous slide. Like on average over a population, what would happen if I took a particular action? Now, this is fine, but it's actually, scientifically speaking, not the most interesting topic that I might want to approach, right? So doctors are more likely to prescribe certain treatments to certain subpopulations. So let's say that I'm prescribing blood pressure medication. Well, in that case, what I might be interested in saying is like, of the patients with high blood pressure, what would happen if I intervened to give them blood pressure medication, okay? So this is a conditional average treatment effect. I'm conditioning on the patients having particular properties and saying, conditioned on the patients having this property, what would happen if I perform this intervention? All right. So this is a much more interesting question scientifically, because this is the kind of question that we're actually interested in asking in practice, not, on average over a population, what would happen if I gave a certain treatment? Okay. Now, another thing that I'm going to discuss is something which is a counterfactual, so average treatment on the treated. So of the people who receive pills, what would happen if I gave them surgery? So this is like a thought experiment. And I'm going to go into a little bit more detail about that later on in the talk. But the causal framework allows us to make these kinds of thought experiments. Then I'm going to talk about something called a mediation effect, which is if I've got, let's say, two ways in which a cause can affect an outcome, one which is direct and one which is indirect, which of these two paths has the strongest influence? Is it the direct path? Is it the indirect path? And this is something I'll talk about. Finally, I may briefly talk about something called proxy methods, which is what happens when the context is hidden. So it was very important, of course, to see the context of our actions when we're trying to determine the outcome of an action. If this context is hidden, then we need to take other approaches. Okay, so I said at the start that I'm going to be using kernels for this approach. What is the advantage of using kernels? One big advantage I would say is that you can define your variables on any domain where kernels exist, right? So my treatments, my covariates, and so on, these can be basically any variables on which you can define kernels. So if my treatment's continuous valued, if my treatment's high dimensional, as long as I have a good kernel on my treatment, I can use this high dimensional treatment. So if my treatment might be a vector in RD, for instance, like it's a number of different medicines and each of the medicines has a dose, I can deal with that. It's not just a question of saying a binary treatment where I do or don't give a pill. Okay. Likewise, my covariates can be quite complicated. It can be sort of age, demographic information, and so on. As long as I can define a kernel on it, I can do causal reasoning with it. Another great advantage of kernels is that most of what I'm going to describe has a one-line implementation. So it's very, very straightforward to implement. And we also have, and I'm going to talk about these, some very strong statistical guarantees. So basically, I have guarantees that as I see more data, my answer is going to get better under some very general smoothness assumptions. Okay. For those interested, we have also implemented everything using neural net features. So that's obviously not the topic of this talk, but we have papers where that's also done. Okay, any questions so far? Great, okay, no questions so far. So I'm going to make one modeling assumption, and I'm going to use one algorithm throughout the whole talk. So this is a very easy talk. It has one assumption, one modeling assumption, and one algorithm, and that's it, okay? Our modeling assumption is that all of our functions can be written as linear combinations of features. Now, as I said earlier, I can use finite dictionaries of neural net features, but I'm going to focus in this talk of infinite dictionaries of features, which I'm going to basically employ by using kernel methods, all right? Now, if I have an infinite dictionary of features, I don't want to have to write them down explicitly, but what we're going to find is that all of the algorithms I describe in this talk can be written in terms of the dot product of features of my training points and features of the point at which I'm evaluating. So basically, I don't ever have to explicitly write down my infinite dictionary of features. I just manipulate all of my features via dot products of features with other points. And I can do that using kernel methods. So as I think the audience of this talk knows very well. So the primary focus of this talk is going to be the kernel approach. All right, so this is my modeling assumption. All functions in this talk are going to be RKHS functions. And I'm going to fit every single function in this talk using just one algorithm for the whole talk. And that algorithm is ridge regression, so kernel ridge regression. So in this case, I've got my RKHS function of my features. I'm predicting my Y, some outcome using this function of X. I'm doing this over some training data. I've got an L2 loss, so a squared loss here. And then I've got this additional ridge term, which is penalizing the RKHS norm of my function here. Okay, so I'm in infinite dimensions, and I never want to explicitly represent my features. So I somehow have to represent the solution to this problem entirely using dot products of features of my training points and dot products of features of whatever point I'm trying to evaluate my function at. Okay. Now, I think the audience of this talk is going to be very familiar with the following result. The regression solution can be written as a weighted sum with weights alpha I of these kernels, right? These dot products between features of xi and features of x. Now, let's say that my kernel is a Gaussian kernel, okay, exponentiated quadratic. And let's say that my alphas, I've got some positive alphas, I've got some negative alphas, and then the green function is a weighted sum of these kernels centered at xi, evaluated at x, right? Evaluated at some point on the x-axis. And this is a function that I get, which is a solution of this ridge regression problem. These alphas can be written as a basically a matrix product of this k, which is the kernel between my training samples. So each xi and xj gets an entry here, and then this vector of y's, which are my vector of observations. Okay. Ridge regression solution, I think everyone here knows this pretty well. This is not the way I'm going to write this solution. Okay, so now I'm going to surprise you. This is the way I'm going to write the solution. Now, this is mathematically completely equivalent. There's nothing that I've done that's different here. But what I've done is I've expressed this in a slightly different way, like not the way that you're used to seeing it in textbooks. I've said that my prediction at x is now a weighted sum of beta I of x, right? So some vector, which is a function of x, of these yi's. So I've taken a weighted sum of yi's using weights beta I, which depend on my x, okay? Now, the expression for beta as a function of x is just this expression here. which is the same kxx plus lambda I matrix from before, but now I've got this vector of dot products of k's of xi and x, okay? Now, I've done nothing different here, right? This is mathematically completely equivalent to the expression I had before. However, writing my solution as a weighted sum of my yi's is going to be very useful to me later in the talk. Okay, so later in the talk, we're going to see that this form is actually a much more interpretable form when we get to some slightly more complicated settings. Okay, any questions so far? Okay, great. That means it's very clear. So I'm going to now give a consistency result. What this means is that I want to basically demonstrate to you that in the case of ridge regression, as we see more samples, we're going to get a result that is going to improve, okay, and get better and better. Now, this is, why am I explaining this consistency result? It's because all of the results in the talk that I'm going to give are going to come with these very strong guarantees. And so I want to basically emphasize to the audience what these guarantees look like and how, in fact, they're quite easy to understand and they make a lot of sense intuitively. Okay, so this is going to be, the next couple of slides are going to be a bit mathematical. So I, again, emphasize that it's important to ask me questions if anything's not clear. Okay, so in order to describe the guarantees, the consistency guarantees that we get for this ridge regression solution, I'm going to need to introduce a little bit more notation about this RKHS norm of my function here, okay? Now, the next two slides are going to be basically describing in notation what this norm means, and then once we understand what this norm means, I'll be able to give you the consistency guarantees. Okay, so to describe what this norm means, I'm going to take my kernel function, right? And I'm going to do an eigen decomposition of this function, right? So I'm going to find eigenfunctions, E, and eigenvalues lambda, which satisfy this eigenvalue equation here, okay? So this is a property with respect to some probability measure. The probability measure here just has to be any probability that covers my domain. So if I'm in the real line, it could be like a Gaussian. This is just some reference measure, okay? I'm going to find my eigenvalues. I'm going to find my eigenfunctions. Now, given my eigenvalues and eigenfunctions, just as in the matrix case, I can express my kernel as a weighted sum using the eigenvalues of this product of eigenfunctions. So this is just like an eigenvalue decomposition of a matrix, but I'm now just doing it with my kernel function. All right. So this is an alternative expression for my kernel. Now, why did I do this? Why did I write my kernel in this form? The reason I did is because I can now express my RKHS norm as a function of these eigenvalues here. Okay, so let's do that. Let's say that I have a function which I've written as a weighted combination of these eigenfunctions from the previous slide. So f of x is a weighted sum of these ELs. Okay, and I've got another function as well, which I've written as a weighted sum of these guys. Okay, now the standard L2 dot product between these is just the weighted sum of the coefficients f and g. But the RKHS dot product has this additional roughness penalty term, right? So my lambdas are eigenvalues, they're decreasing. That means that the reciprocal of the lambda are increasing. And that means that when I take my RKHS norm, I'm penalizing coefficients for, for very high order eigenfunctions, right? Which are generally less smooth, okay? So this lambda means that my RKHS norm gives a greater penalty for less smooth functions. Now I'm just going to pause here because I covered quite some mathematics. Is there any questions about this? Okay, great. So this is my RKHS norm. Okay, and that's the norm from a couple of slides ago takes exactly this form. Now I can further go and say I can define a subspace of my RKHS, a smooth subspace of my RKHS, basically by ramping up the amount of penalization that I'm applying, right? So this C parameter says, how much smoother am I than my RKHS? The bigger the C, the smoother the function. Okay, so I'm starting with my RKHS norm, and then I'm saying, well, here's a hierarchy of smoother and smoother and smoother functions of that RKHS. Okay, so I've defined my RKHS, and I've defined smoother functions in my RKHS. Now, using this, I'm able to give you my guarantees, okay? So let's say that the function that I'm trying to learn is in one of these smooth subspaces of my RKHS. Okay, So basically, the smoother my function is, the easier it will be to learn. If it's in the RHS, I can learn it. If it's in a smooth subspace, I can learn it even faster. Now, that is one of the factors that determines how easy my function is to learn. Another factor is how big is the space I'm mapping from? And that second thing can be determined by basically the decay of the covariance of my features, right? So if my decay of my covariance of my features is very, very fast, that means I'm kind of mapping from a small space. If the decay is small, I'm mapping from a big space, okay? So basically, the consistency guarantee I have says that as my function is smoother, and as the space that I'm mapping from is smaller, I'm going to learn as n, the number of training points I see, goes up faster, okay? So it's an easier problem to learn. If my space is big or my function is not smooth, then I'm going to learn more slowly. The very best I can do is that my error improves as n to the minus 1/4. Okay, so that's like, the easiest I can do. Okay. And this guarantee can't be improved on. This is a minimax guarantee, which is to say that like this is the fastest it's possible to learn. This is the result by Fisher and Steinwart. So this is basically a very, very strong guarantee on the results of ridge regression, saying that I'm able, basically, as I see more samples, to learn that function at this rate at best. Okay, are there any questions about this?
What does that P represents here in the order notation?
Oh yeah, so this is basically convergence in probability. So this is a way of saying, yeah, exactly. Yeah. Is there any other questions?
I actually have one.
Yep.
So if you can hear me, great.
Yep, I can hear you.
Oh, great. So what would be the advantages over some type of dimensionality reduction in this case when you're smoothing with these functions?
Right. No, this is actually a very good question, right? Because nowhere in this equation has there appeared the dimension of my space, right? So it's like, well, is this really a dimension independent result? The answer is that in kernel methods, we are a little bit sneaky and we're hiding dimension elsewhere. So basically, if you remember so one example of a kernel class that one might consider is a Sobolev space, okay? And the Sobolev space, you can sort of say, well, the Sobolev space is an RKHS when the amount of smoothness is greater than dimension on 2. Okay. And effectively, that sort of puts a minimum smoothness on your functions, which becomes more, I think, restrictive as dimension increases. And so in this case, what you can find, and this is actually explained in this paper here, is that as dimension goes up, the rate at which you can learn your function goes down. Or alternatively, you have to enforce greater smoothness as dimension goes up to retain the same rates. So basically, the dimension absolutely affects how fast you can converge, but it's hidden actually in this, I guess, notation here. So this sort of requirement of being in a smooth subspace of the RHS becomes more restrictive as dimension increases.
Yeah, thank you.
Very, very good question. I like that question very much. Yeah. Any other questions? Okay. Great. So this is our guarantee for good old ridge regression. Now let's we've sort of introduced all of the required background. Now let's continue and onto the problem of causal effect estimation. Okay. So causal effect estimation using ridge regression and kernels can be done here. So this is a biometric paper that was published a couple of years ago. Or we can use neural net features, but of course, for the purposes of this talk, we're going to focus on kernel features. And I emphasize all of the code is downloadable here, so you don't have to implement any of this yourself. You can pretty much download and use it right away. Okay, so remember from the beginning of the talk, my average causal effect, right? Which is I've got my conditional mean of my outcome given my treatment and my covariates, and I've just averaged that over my population, right? Average causal effect. Now, I'm going to need to make some assumptions, but all of these assumptions that I'm going to make are actually common sense. So none of them are strange assumptions. Okay, the first assumption, stable unit treatment value assumption, what that means is that the pill that I take can't cure the person next to me, right? So any treatment affects only the individual treated. So in medicine, I think that's a reasonable one. Okay, conditional exchangeability, y superscript a, so the effect of this intervention, is independent of my observed a given x. What that amounts to saying is that there's no additional hidden covariate v out here affecting both a and y superscript a, right? There's no additional hidden confounding is what that's saying. Now that's a strong assumption, and it's an assumption we can weaken later, but for now we're going to assume that this assumption holds. Okay, finally, overlap, right? Overlap means that I'm not going to make predictions on things I don't know, or things that I've never seen, I should say. So let's say that I never gave pills to somebody with a severe form of the disease. Then what would happen if I gave someone with a severe form pills? Well, I don't know because I never tried it. So anything that I'm predicting here has to have arisen in my observed data for me to be able to predict about it. Otherwise, I'm just making things up. So I think overlap is a very reasonable assumption. But it's an assumption we have to be very careful of because in quite some data, it may not always hold. Okay, so these are our assumptions. Now, the data set that I'm going to be exploring here is a US Job Corps data set. A is treatment, so number of training hours. Y is the percentage employment. And then X is everything we know about these individuals. So basically, these are individuals, disadvantaged youths, who are being given a training program in order to improve their employment prospects. Okay, so we know a lot about these individuals. So we know how old they are, their education, their marital status, and many other things about them. So all of these things are in this X here. Okay. So at this point, I'm doing regression, right? I've got a conditional mean, which is a function not of one thing, but of two things. It's a function of A, my treatment, and it's a function of X, my covariates, right? Now, previously, when I introduced ridge regression, I had my output being a function of one thing. Now I've got an output which is a function of two things. So what do? All right. So let's say that I have a good set of features of my covariates, and that has a kernel. And let's say I have a good set of features of my treatments, and that has a kernel. Then a valid kernel on this treatment covariate pair, so a kernel between AX and A prime X prime, is a product of these kernels, the kernel on A and the kernel on X. That is a valid kernel, all right? Because it's a sort of measure of similarity of AX and A prime X prime, sort of saying that if A and A prime are similar and if X and X prime are similar, then this product is large. But if either of these is small, then the product is small, like an AND operation. Okay, now the corresponding feature map is basically the Kronecker product, the tensor product of the features of A and of X. So a way of thinking about that is like as a big long vector of products of pairs of features of A and X. So feature 1 of A, feature 1 of X, feature 1 of A, feature 2 of X, and so on and so on. So that's kind of what this feature dictionary looks like. All right, so this is a feature dictionary we've chosen. We've chosen this because it's necessary to use this specific feature dictionary for all of the reasoning that I'm going to describe to work. Okay, but it's not, let's say, too much or too restrictive an assumption. So if I'm, if my kernel on A is Gaussian and my kernel on X is Gaussian, that amounts to sort of saying that I've got a Gaussian kernel on A and X, which is a very rich kernel, right? It's dense in the space of continuous functions on A and X. So that's a very rich function class. So I'm not giving up too much by making this assumption. Any questions about that?
I have one, since
Yep,
you
good.
allow us.
I like questions.
How about these feature functions? Are they the same or could it be different?
So if I use the product kernel, then the I think algebraically, if you're using a Gaussian kernel, you're going to see you literally just have a Gaussian with the concatenation of A and X, and so you're not in this case you're losing literally nothing by doing this concatenation. Yeah.
Phi are the same.
Yes. Yes.
Okay.
Yeah. Yeah. In this case, that's correct. Yeah. What does my solution look like? My solution actually looks like a weighted sum of these y's. So remember this slightly different form of the solution that I described from earlier, right? Where these weights are now a function not just of x, but of a and of x. And what I've got is an entry-wise product of my kernel on A and my kernel on X. Okay, so this is basically my KAA is a matrix of kernels between AI, IJ. Kernel XX is a matrix of kernels between XI, XJ. I take the entry-wise product of these two matrices, and then I take the entry-wise product of these. So the solution is like immediate from the standard ridge regression form when I use this feature map. Okay, so very, very little extra work is needed here. Okay, so this is now my ridge regression solution when I have two inputs rather than one input. Now let's get my dose response curve. So I'm in the well-specified setting. So here my function of a and x is the conditional mean of y given a and x. I'm going to write that as a dot product in an appropriate RKHS. So this is the RKHS with the product kernel. So dot product of gamma 0 and feature A cross feature X. Okay, and now I'm done, right? I just have this regression function. I take the expectation over X, and that's my average causal effect. Finished. Okay, I can take one additional step, which in this case is not useful, but I'm just showing it in order to make slide a bit later in the talk a little clearer, which is that because of this bilinear form here, I can take the expectation inside this dot product. Okay, so now I have the dot product of gamma and the average, the mean of my features of X and my features of A. Okay, tensor producted with my feature of A. So the mean of my features of X is called a mean embedding. It's literally just a vector of expectations of my features. Okay, and this is a representation of my probability. So I take this average of my features of X, take its tensor product with A, evaluate that at gamma 0, and that's my average causal effect. So I can take my average either outside or inside the dot product. Right. Now, fortunately for us, this empirical estimate of my mean embedding, so my sample average of my features, converges to the population of my features at a rate which is very fast, so 1 on square root n. Okay, which is elsewhere it's been shown to be minimax. Okay, it's the best rate you can get. Okay, so here is my average causal effect, and you can see that I've just taken the ridge regression solution, and all that I've done is to average it over my population, over my sample. Okay, now I have inherited from the consistency of ridge regression the following rate, which establishes consistency of my average causal effect. And you'll see here that this rate is basically the ridge regression rate, because all we're doing is we're taking a ridge regression solution and we're averaging it. And the averaging is sort of less important than the speed of convergence of my ridge regression. So that gives me my convergence speed. And you can sort of see it's a function, again, of this smoothness term C and this eigenspectrum decay term B. All right, let's look at some results now for this Job Corps data set. So remember, X is all the covariates, so age, education, marital status, and so on. A is the treatment, so the number of hours the individuals have been in the training program, and Y is the outcome, so percent employment. All right, and what you can see here as a function of this intervention, right? So class hours is an intervention. You can see the effect of that intervention on average over my population on percent employment. Okay, and so what you can see here is a kind of diminishing returns type phenomenon. So you can imagine here, you start as a master's student, then you do a PhD, and then you do a postdoc, get a first faculty position here, become a professor somewhere down here, and so on. So longer you spend, you improve for a little bit, then not so much. What we're also comparing against here is a double D bias approach. Now, it's hard to know the ground truth here because the ground truth can only be found by intervention, but I would argue at least that this sort of more smooth approach is a little bit more plausible than this less smooth approach. And so this is obviously, it's not something we can prove, but it's something that we would sort of argue for in favor of our method. Is there any questions at this point? Okay, great. So now we're going to, I think, a topic which is a lot more interesting scientifically, which is my conditional average treatment effect, my conditional average causal effect. Okay, so in this case, I'm sort of saying, look, I've got my covariates up here, and I'm now splitting them into two. I've got my X and I've got my V. So V you can think of as the thing you're conditioning on. So I'm going to give the example of blood pressure medication, right? What we're interested in is what is the effect of intervening on blood pressure medication, so treatment A, conditioned on the blood pressure having some value. So V is blood pressure has some value. What is the effect of intervening on A given blood pressure of level V? Okay. Now let's say that my individuals have blood pressure of level B, okay, which is high. Now, if an individual has high blood pressure, well, their age is more likely to be in the range, like let's say 50 to 65, and a lot less likely to be in the range, 15 to 20. Okay, so given V takes some value, that also has some influence on the distribution over X. Okay, this arrow here means that I don't take any position about the causal effect between X and V. So it may be, X causes V, V causes X. There might be a hidden common cause. We don't care about how X and V interact. We just know that given V, the distribution over X is going to change in the way that I've just described. And so now we're going to say, look, what is the average causal effect of an intervention A conditioned on V? Conditioning on V will change the distribution over X, and that in turn is going to have an influence on my outcome. Is that clear? Okay, great. So now we've got Y, which is a function of A, and now we've split our covariates into two. So we've got X here, and we've got V here. Okay, so AXV. Now here, my function is a function of 3 arguments rather than 2, but I just use the same tensor product trick. So now I've got a function of A, tensor X, tensor V. Now what I'm interested in is the conditional average treatment effect, conditional average causal effect, which is the outcome of an intervention A conditioned on V taking some value. All right, let's plug our function in. So I take this function here and I plug it in. Now I've got an input A, right? Well, I fix that because that's my intervention. I've got V. Well, V given V is just V, right? nothing interesting there. But now I have a random variable X. And as I've said earlier, the random variable X is going to change its distribution conditioned on V. Okay, so now we have a question. How do we take these conditional expectations? And there's lots of different ways of doing it, right? I could do a density estimation of X given V, and then I could sample from it, right? That's valid. Or I could use a GAN. I could use whatever my favorite generative model is. But if I'm doing that, it feels like I'm solving a harder problem than the problem I need to solve. Because what is the actual problem I need to solve? It isn't density estimation, which might be in very high dimensions, right? The problem I literally need to solve is the conditional mean of the features of X given V, right? That's the actual problem I need to solve. So as Vladimir Vapnik said, don't ever solve a harder problem than you need to solve. And so literally this is what we're going to do. The problem we're going to solve is to compute the conditional mean of my features of X given V. So this is going to be called a conditional mean embedding. So this is like, just as a mean embedding is a representation of a probability, a conditional mean embedding is a representation of a conditional probability. So it's a conditional mean of features of X given V. Any questions about that? All right, so now what we need to do is to learn the conditional mean of features of X given V, okay, from data. So now I'm mapping from a feature space to a feature space, right? I'm getting a conditional mean of features of X given V, and I'm doing that by taking an operator E and applying it to my features of V, okay, to get my conditional feature mean of X given V. Okay, so it's an operator because it's mapping from a feature space to a feature space, whereas the regression function just maps from a feature space to the reals. Now, since I'm learning an operator, I need to place some sort of smoothness restrictions on the operator, much as I had to do when I was learning just a regression function. Now, the restriction that I'm placing is that my operator is in the completion of the span of outer products of features of X and V, okay? Or in other words, it's a Hilbert-Schmidt operator on those spaces. So that's a rather difficult smoothness assumption to interpret. I'm going to give you a nice and somewhat simpler understanding of this, which is as a smoothness assumption. Okay, so let's say that I have an RKHS function of features of X given V, right? And H is just some RKHS function on X. What I'm saying, my implied smoothness assumption that this assumption implies is that this conditional mean of features of X given V is in the RKHS on V. So my expectation of functions of X given V is changing smoothly as my conditioning variable changes, right? And this is what makes it possible to learn, right? If my conditional mean of H of X changes smoothly with V, then I can learn it. if a tiny change in v makes the conditional mean of h to x given v change completely, then it's impossible to learn at that point. Okay, so this is a smoothness assumption we're making. Is that clear to everybody? Okay, so the conditional mean of functions of x given v is varying smoothly with v, so we call E a smooth operator, which is my dad joke for this talk. All right, how do we learn the smooth operator? Well, the way we do it, there's only one algorithm in this talk, ridge regression. Everything is ridge regression here, okay? So I'm doing ridge regression from features of v to features of x using the operator E. It's again a squared loss, but it's a squared loss obviously in my output space h of x. And then I have a norm here on E, which is basically a ridge term, right? The Hilbert-Schmidt norm, the sum of the squared singular values of E. This is just an L2 norm on my operator E. Now, it seems that I've just written something that is very hard to solve, right? Because E is mapping from an infinite space to an infinite space. So how on earth do I represent this solution here? Okay, I can write it down as ridge regression, but how do I actually solve this? So it turns out that the form of the solution of this ridge regression problem takes exactly the same form as scalar ridge regression, okay? So my empirical conditional mean of features of x given v is just a weighted sum of my features of my training x with weights which are exactly identical to the scalar case. Okay, so solving for this mapping from feature space to an infinite feature space is no more difficult than solving from a feature space to a scalar, right? Same expression when we're using ridge regression. And this is under this assumption here. All right. Now, once again, we have consistency guarantees, okay? Now, in this case, what we're doing is we're sort of saying we're mapping to a feature space of hx, but what we're going to do is we're going to say that the functions in x are varying smoothly with the input v, right? And so this C applies only to my v space, right? Because I'm always mapping to the same output space, but I'm mapping from a smooth subspace of my input space to my output space, okay? So once again, when C is big, my function is smooth, the problem gets easier. And then also, of course, the consistency depends on the size of my input space, which is given by the eigendecay also of my input features. And then, remarkably, the result that we get on consistency for this smooth operator is the same as for ridge regression. Okay, so this is fantastic. It only depends on basically how quickly how smooth my function is as a function of my inputs and how quickly my input space decays. And so you can see this result here is exactly the same as the result from earlier. So I'll pause here. By the way, this is a minimax result. So again, it's the fastest result you can get. Any questions?
I actually have a question, which is actually on the previous slide. Could you elaborate a little more on why the assumption is needed and what would go wrong if the smoothness assumption is not there due to the or its effect to the ridge regression solution?
Yeah, so basically, when we write this, what this implies is that E is a Hilbert-Schmidt operator, so it has a bounded Hilbert-Schmidt norm. If it didn't have a bounded Hilbert-Schmidt norm, then you couldn't actually compute the regularizer. So it's sort of like saying, you know, I'm in an RKHS, basically. So that's, yeah. Now, what's, I think, interesting about our consistency result, which I haven't talked about in this talk, is like, well, what happens, you know, a conditional mean is just a square integrable function on my feature space of x. So it's, you know, it's an L2 mapping from v to x, right? Which might be outside of an RKHS. So then the question is, if I have a function outside the RKHS, but I'm approximating it with a function in the RKHS, what does that mean for my consistency? What does that mean for the rates? Now, in this paper here, what we do is we define consistency results as we interpolate from the RKHS to the L2 space. And what we've shown is that you still get consistency, but that the rates get worse, let's say the less smooth your function becomes. So as your function sort of goes from being in an RKHS with a finite Hilbert-Schmidt norm to a space of square integrable function from v to x, you're going to learn slower. So that's the answer. Yeah.
Thank you.
Cool. Any other questions? Okay. Great. So we have now, I think, a really nice guarantee on the smooth operator. What does our conditional average treatment effect look like? Well, it looks exactly what you'd expect. So if I just go back a bit, what I've done is I've taken my ridge regression and I've plugged into it my conditional feature mean of features of x given v, right? And so what's our conditional average treatment effect going to look like? Well, I've got my regression, which is mapping from A and X and V to Y, and then I plug into it as input my conditional feature mean of X given V, which is the result of that smooth operator equation. So the conditional average treatment effect, I can literally write in a single line of math after I've computed my kernel matrices. So this is really satisfying. And do I have guarantees? Well, yes, I do. The guarantees are basically very straightforward here. I assume that I'm using the same n number of samples for my conditional feature mean and for my regression. And then what I have is I've got two terms. This term tells me how fast I'm learning my conditional mean of y given ax and b. So this one here. And then this term here tells me how fast I'm learning my conditional features of x given b. And so these together determine how quickly I'm learning my conditional average treatment effect. So we've got, again, thanks to the fact we're using kernel methods, some very nice and strong guarantees on the consistency of my conditional average treatment effect. So let's have a look at what this looks like for our Job Corps data set. Here, V is age. So we're sort of saying condition on age, what is the effect of the people taking some number of hours of training, okay? And then X is everything else, okay? So X is, marital status, education, and so on. So if somebody is, let's say, 16 years old, it's less likely they've been to university. If they are 26 years old, it's more likely they've been to university. So education is going to have a different distribution depending on age. All right. So now what we've got is a basically some sort of a contour map where on the x-axis we've got the number of hours, class hours, so that's our intervention, and then on the y-axis we've got age, which is something we're conditioning on. All right, and so we're looking at the effect of an intervention on the x-axis conditioned on age on the y-axis. And what you can see that you can sort of slice this contour at different ages and get different results. So let's say you slice at 16 years old, you see employment increasing from 28% to 36% as I move along this axis here. Okay, if I slice at 22 years old, employment increases from 40 to 56% before going down again. So what you can kind of see here is that, depending on the age, you're going to get different outcomes. And so if I'm a policymaker and I'm allocating resources, then I might choose from a graph like this to allocate more resources to certain age groups than to others, because that's going to give me a better outcome. All right, any questions about conditional average treatment effects? Okay, so now we're going to do a really fun exercise, which is a counterfactual. Okay, this is called the average treatment on the treated. Okay, now what does that look like? This is the expectation of y under intervention A prime conditioned on A taking a value. So what on earth does that mean? Okay, the way to understand this, I'll give the example in respect of the medical example we started the talk with. Of the patients who received pills, what would happen if we gave them surgery? Okay, so why is that a reasonable question to ask? Well, if the patients had received pills, then the distribution over X gives more weight to a mild form of the disease and less weight to a severe form. Okay, so of the patients who received pills, it's more likely the form of their disease was mild. If we intervened to give those patients surgery, they probably would still be cured, right? They've got a mild form, so surgery is way more than you need, but it's probably going to cure them. You could do the other counterfactual. Of the patients who receive surgery, what would happen if we gave them pills? Well, they receive surgery. The form of the disease is more likely severe. If we gave them pills, it's more likely that they would not recover. Okay, so you can kind of see it's a thought experiment. It's not that you can sort of take these people and take the pills out of them and give them surgery, but it's a thought experiment. Like, what if we'd done something different to that population than what was done historically? And this is, again, like a really interesting question to answer, if one is sort of talking about data analysis. Okay, so this is the meaning. Yep.
Depending on the administrator of the hospital, doctor might decide the best, I guess.
Well,
may not be only the thought example.
Yeah, no, exactly. So there could be some real world consequences of this thought experiment. But it's a very, I think, worthwhile thing to ask about. So it's sort of like a conditional average treatment effect, but we're conditioning on A rather than on V. So this is the best way to think about it. But as a way, like as a lens on your data, I think this is a really interesting and worthwhile experiment to do. It's like, what would have happened if I'd acted differently? I can sort of go back and run the experiment in my mind. Okay, so let's look at this, right? So I've got my, my function of a prime, which is my intervention, and x given a. But as I mentioned when I described the slide, x given a has basically a distribution which is tilted, right? It's not just a marginal distribution on x; it's a different distribution on x depending on the treatment that we're given. Okay, so now what do I do? Well, I just take the expectation inside, and I've got my conditional feature mean of x given a. Okay, and we learn that we have a smooth operator. We know how to learn this thing. Once again, once you have this expression here, the empirical expression is immediate, straightforward, right away, right? I've got my regression from a and x. Okay, my regression from a and x, and then I plug into that my intervention a and my intervention a prime, and then my conditional mean of features of x given a. Okay, and there we go, one line of code, very straightforward. So my average treatment on my treated is just as easy, if not easier, as my conditional average treatment effect. Okay, so one last example. This is mediation analysis. So this is actually, again, like an example where I think has quite some scientific interest. When there are two ways in which treatment can affect outcome, so a direct path and an indirect path, the question is, like, which of these paths is the strongest? Is it the indirect path or is it the direct path? Okay, so I'm going to give an example again from the Job Corps data set. Okay, so X is all of the covariates that we have. Okay, A is number of training hours. M is employment. Okay, M was, Y before is now M, and then Y is the chance of being arrested. Okay, so there are basically two paths from taking this course to lowering your chance of being arrested. One is, when you take this course, you're less likely to be arrested. The other is when you take this course, you're more likely to get a job. When you're more likely to get a job, you're less likely to be arrested. Okay, so the question is, like, is it because you're more likely to get a job that your arrest chance goes down? Or is it because when you take this course, like, you're learning better life skills, and that makes your chance of being arrested going down? Okay, so you can see here y is a function of three things: a, right, m, and x. Okay, so now I've got my regression. It's got three inputs: y, a, m, and x. Now, what we want to do is to somehow decouple the effect of a on y and the effect of a via m on y. Now, this next thought experiment is the hardest one in the talk, so I'm going to definitely pause for questions after I describe it. What I've got is something called the mediated effect. Now, this is y under intervention A and this distribution of m with green A. So what on earth is going on here? Okay, so what I want to do, basically, to decouple the indirect and direct paths is basically to change m in a way that's somehow independent of the direct effect A on y, right? So what I could ideally do is basically say, well, I'm going to sort of move m in ways that are independent of the direct treatment A. So I'm going to change my employment in one way, but then I'm going to change the number of hours in my course in another way, and I'm going to decouple these two things. And when that happens, do I get a different effect than when I don't decouple these two things? Does that make sense? Any questions about that? Okay, so how is it that I change m? right? Now I can't change M completely arbitrarily. Let's say, employment, I make it something completely crazy, like, oh, I'm employed, 80 hours a day or something like that. The only way that I have to make realistic changes to M. Now, the realistic changes to M that I make are changes that I could make through the actions that I'm allowed to take. So employment, I can change employment by making my individuals take more or fewer hours of class. Like, those are the plausible changes in employment that I'm able to create, okay? And so that's what this is here. This is a sort of distribution over M that's possible to achieve by the actions I'm allowed to take. Is that clear? Okay, so I'm changing my distribution M only in a plausible way using this lever A, but then a direct effect of A on Y I'm doing with intervention A prime, right? So I'm saying, look, I'm going to change my chance of being arrested as if I'd taken A prime hours of courses, but my employment is as it would be if I took A hours of course, okay? So in other words, my distribution of M is going to change independently of my A prime here. So I'm going to pause now and just let people think a bit about that. So are there any questions about this? Right, so normally because of, A would influence M and Y directly, I wouldn't be able to change this M distribution without also changing the direct effect of A on Y. But in this thought experiment, what I'm saying is, well, I'm going to change M as if I could change it independently of the direct effect of A on Y. The way I'm doing that is I'm changing M using one A, the green A, and then doing the direct effect using this orange A prime. Okay, now if that gives the same answer as if I put a green A here, then basically, that sort of tells me something. But yeah. Okay, so how do I compute this? Well, again, using conditional feature means just as before. So I've got my conditional feature mean of M given A, and then I basically compute the average out over X, and then I evaluate that at A prime. So again, the implementation of this is very, very straightforward. Okay, so this is our mediated effect. Now let's see what that means for the Job Corps data set. Okay, so I'm going to see what this means for my Job Corps individuals, and we'll see if this mediated effect tells us whether the direct path of A to Y is the most important one. So taking that course means I'm less likely to be arrested, or whether the indirect path is most important. So in fact, the main reason I'm not being arrested is because I'm employed. Okay, so we're going to now distinguish these two. Okay, first of all, we're going to compute the total effect, right? So the total effect is sort of saying if I change my intervention from A to A prime and I don't decouple the direct and indirect paths, right? So I take exactly the same indirect and direct paths, then what is the effect going to be? Okay, so it's sort of saying, look, overall, I don't care if the path is indirect or direct. If I increase the number of hours, how much less likely am I going to be arrested? Okay, so in this case, if I increase my hours from 480 to 1600, I have a 10% chance of reducing being arrested, right? So I can sort of move up this axis here, and I go, from 480 up to 1600, and you can see I get this nice reduction in the chance of being arrested. So that's really nice. Okay, now this isn't decoupling the direct and indirect paths. You can see I'm using the same A here as here. Okay, so I don't care if that happens via direct or indirect paths. I'm just saying, if I do this intervention, how much less likely am I being arrested, regardless of whether the effect is direct or indirect? Is that clear? Are there any questions about that? Okay, now let's see whether the direct or indirect effect is the most important. So here, my distribution of M is not changing. It's going to be basically as it was before. And so the only effect that's changing now is this direct effect, okay? So I'm basically saying, treat M here as if I use the old A, but then use a new A to influence Y. Okay, so this is sort of saying, now I'm only allowing the direct effect of A on Y, and I'm freezing M. And guess what? These graphs look exactly the same. So what we've now established is that it's actually the number of hours that the students are spending in the course that is having the biggest effect on the outcome. And it's not because of the change in the employment. Okay, so the indirect effect, what we established here, is effectively zero. And in fact, it's the number of hours that the students are spending in this course that is directly influencing how likely they are to be arrested. Are there any questions about that? So, this is, again, like really interesting if you're a policymaker, right? Like, you're trying to influence a population of individuals to reduce their chance of being arrested. What should you do? Should you make sure they get in jobs, or should you make sure they take this course? And the results that we found indicate that they're better off, like you're better off allocating funds for the individuals to take this course, because this is what's influencing their chance of being arrested. So I've got something actually very actionable out of this result. All right. Just as a final thing, we also have something called a dynamic treatment effect, where we have a sequence of actions which influence both the future covariates and the outcomes. So in medicine, you often don't treat somebody once, you give them a sequence of treatments. This is also something we can model, and this is in the papers as well. So I think I'm coming to the end of an hour. So what I'm going to do is I'm just going to skip forward to the conclusions. So in conclusion, what have we done? We've used kernel methods to give solutions for average treatment effect, average treatment untreated, conditional average treatment effect, mediation analysis, dynamic treatment effects, and we can also deal with the case where covariates are not observed, but I'm not going to go into that. We've done this with kernels, which has a number of really pleasing consequences. One is that the treatment, covariates, and so on can be defined very richly. Wherever I've got a kernel, I can then define variables on it. The solution, so if A is continuous valued, if A is multidimensional, it doesn't matter, because as long as I've got a kernel, I can deal with those things. It's a simple, robust implementation, so the only thing that we've had to worry about is ridge regression, which is great. And because we're doing kernel ridge regression, we've got these very strong statistical guarantees. So this is really nice. There's some topics that we haven't covered in this talk, which I'll leave out. Notably, we can also do this with adaptive neural net features, not just kernel features. So sometimes, let's say if my treatment is an image or a text, it might be better off using neural net features for those. Great. So we've got some selected papers. The work was supported by the Gatsby Foundation and Google DeepMind. And I'm now happy to take additional questions. So thank you.
Thank you very much, Professor Grithen. Is there any question? Further questions?
Oh, I see a question.
Hi.
A hand is raised. Yeah. Mm-hmm.
Yeah, I was wondering regarding the mediation effect, to what extent is it different from trying to just sample from the variable m, the marginal of m, and compare effect on the marginal of m, just to see if it has an impact, and then just say that it's whether it's pertinent on its own or whether we have to go through this indirect way through the action of A?
Yeah, no, that's a good question. You can sort of say, rather than having, let's say, the A influencing the distribution over M, and then that in turn influencing Y, you could just say, look, marginal on M, and that's enough. I think that, can you see my slide still, by the way?
Yes.
I'm going to scroll. Oh, very good. Okay. So a reason that I'm looking at the condition of M given an A rather than the marginal of M is because in a way, the effects that we aim to observe is basically like, what we want to do is to intervene, like we want the effect of an intervention. And so there are two effects that the intervention has. One effect that the intervention has is on the distribution over M, and the other is directly on Y. And so if the question is like, what is the effect of an intervention? It's, I think, meaningful to look at, the conditional distribution of M given that intervention. So it's sort of saying, look, I've got my observational data, gathered a bunch of data, then I said, okay, I'm intervening now. Now, one intervention I can do is on M via A. and then another intervention directly on y is a prime. And then I'm sort of interested in, let's say, how, let's say different this expression here is, where I've used one intervention to change the distribution over M and another to influence y, over this case, where it's basically the same A for both. So it's sort of like it's addressing a very specific question that the practitioner will have, which is like, where is my intervention having its influence?
Yeah.
Whereas, your question is also an interesting one. It's sort of saying, look, if I just have some distribution over M, and then I have this direct intervention on Y, what influence does that have? And that could also be an interesting question. But it's a slightly different question to the one I'm answering here. Yeah.
Yeah, I got that. Thanks a lot. I have a second question, if you don't mind.
Yep. Yeah.
It's about the comparison to this debiasing, double debiasing result in the literature. Do these people have theoretical bounds like you do for kernels? And can we compare them directly?
Yeah, so I think it's a little hard to compare them directly because there's quite a few moving parts. So one of the complications of the debiased approach is that the inverse propensity score weighting approaches, that are the classic debiasing approaches, are not designed for continuous actions. So when you're using them for continuous actions, you need to make some modification. What they have done is to basically say, look, my action is no longer a delta function at some A, it's actually a Gaussian around that A. And that Gaussian is fairly, we'll sort of think of a limit when it becomes very narrow. So it's a little bit hard to sort of let's say, it's very hard to sort of take those assumptions and translate them into our setting, or take our setting and translate them into that setting. So that's, yeah, I think it's a little bit difficult yeah.
I see. So, but would you say that because of what you said, like they are doing some sort of Bayesian prior, some smoothing, I would say, with this Gaussian averaging, so that's why they would get some smoother estimator than you? Or?
I think, it's a little hard to, so they are indeed smoothing the action, but they're also using a quite different expression. So we've literally got this sort of average of our conditional mean. Whereas what they've got is they've got sort of that, and then this propensity estimator. Because you're sort of dividing by the propensity, it's not super obvious whether you're less or more smooth, basically. So if you sort of look at the correction that they're using, it's not at all obvious what the overall effect of this is. Yeah.
Okay, thanks a lot.
I think at this point I can, if there's no other questions, I can tell you something that our another guest, Aurelian, will talk about later on in March, I guess, on the operator valued kernels from the historical perspective, as well as in the general localized variants. So that might be helpful in also understanding some of the parts of Professor Grethen's talk, especially when we do the distributions over there in the formulations. So that might be very interesting. And
no, absolutely. I definitely agree.
I cannot see Aurelian here, but as we correspond as our correspondents, I know that he's going to give some talk on operators and kernels together, from starting with the historical part. We will turn back to the beginning of 1900s, and that will be interesting. And I know that our audience will be able to join those concepts of yours, as well as how the kernel methods improved from the very beginning of 1920s, I guess. So is there any other question from our audience?
I see one. Yep.
Yeah.
John,
so
please.
I actually have a more hypothetical question, not much related to the talk. So it concerns my research. That's why I kind of want to ask about that. So
sure.
You spoke of interventions. I mean, so what comes to my mind is, can these techniques be used in things like reinforcement learning? Maybe if you have a Markov decision process and then you would want to use these kernel techniques.
Absolutely.
Are there any kind of research directions there, or how maybe?
Yeah,
you
that's
would kind
excellent.
of picture that idea.
Excellent point. Yeah, no, 100%. So one of the, I think, interesting things in causality is that causality and reinforcement learning are like incredibly closely meshed. And many of the tools that apply in one apply in the other. So one, I think, very clear instance where this applies in reinforcement learning is on off-policy evaluation. So basically, like you're gathering data under one policy, and then you're switching to another. So going back to the just average cause effect, here, right, it's like I'm doing a very simple policy. So I gathered my policy under some distribution of A given X, right? So my distribution of actions given my context. But then I'm evaluating under a new policy. And this policy is not a very smart one, right? This policy is just saying, take action A, no matter what, okay? But what if I did a soft intervention, which is to say, what if I used instead here a policy of A given X, right? That would be valid. And I could use all of the tools here to do that. So you could absolutely use this for like, off-policy evaluation of some new policy. This is 100% the case. So this is a simple answer. The other thing is, and this was not covered in this talk, in the event that the context is hidden, we have an algorithm called instrumental variable regression. Now, instrumental variable regression turns out to be extremely close to least squares temporal difference learning and reinforcement learning. And so you can use a kernel instrumental variable regression approach in order to do least squares temporal difference learning, or you can use a neural net one. So this is something that we've done. And so again, like this is an instance where the tools that I've described apply directly to reinforcement learning. So I think in summary, there's a really rich set of RL tools that we can tackle using the approaches that I described today. Yeah, absolutely. For the, I think for the IV case, for the instrumental variable case, I gave a talk at AI Stats. You can find that on YouTube, where I described that in the second half of the talk. So you can have a look at how that works. Yeah.
Thank you. Thank you. That was very nice.
Thank you. Anybody else? So thank you very much, Arthur Griffin, for this nice talk and sharing your knowledge with us. Some people are clapping. I don't know how to do this. So
there's maybe a button somewhere.
I thank you very much, and I will stop recording. We can discuss anything we like.
Yeah, well, thank you
By
for
the way,
inviting me.
generally we upload these videos without any edition, just raw materials. So I'm just, how do I stop this recording?
Yeah.
So thank you very much again.
I'm happy for the video to upload. Yeah, I think that's yeah. It's good to have the questions as well because yeah, then it's more interesting for the listeners. Yeah.